Our next speaker is Manuel, and he's talking about float self-tagging.
Okay, hi everyone. So let's consider a fully polymorphic language, such as JavaScript, where you can define the identity function. This function, you can apply it to all the values of the language, so a number, a string, or even itself. So somehow, this requests that you have a uniform representation of your data structure. If you compile to C, as we will do for the sake of simplicity in this talk, what the identity function will look like. It will take a parameter of some type, OOPSLA'25, and the natural way of representing this value in C will be to use a pointer to something. Probably it will not be a void star, it will be something else. It will be something like a union. And your union will have a header field describing the type of your value and a payload. This is very classical. Let's take an example. How do you implement fixnum with these settings? You have a function that creates a fixnum, it allocates a chunk of memory, it sets the header, so you are able to recognize that it is a fixnum, and you store your actual fixnum in the value, in the box. How do you implement the predicate? Is something a fixnum? Fixnum P, you just check the header and you check if it's the header of a fixnum. How do you make some computation? You extract the value from your boxes, you make your computation, you create a new box, you store it. Super classical. The problem with this encoding is that you have a performance issue because you have transformed a program that was supposed to compute integers into a program that allocates something in memory. So you have some ways for working around that. The first one may be to just pre-allocate small fixnum, and it will be extremely effective for instance, the indexes of your arrays. But maybe you can take benefit of the constraints that are imposed by the hardware regarding pointers. And on our machines, if pointers are correctly aligned, so meaning that they end with a 0, and so if you are willing to trade a little bit of some fixnum, that is to get rid of some fixnum, you can use this alignment constraint to have a more efficient encoding. And typically, in our machine, a pointer will end with a 0, and maybe you can use values that ends with a 1 for representing fixnums. And if you do so, you are able to access a much more efficient implementation for fixnums, and basically, by doing this kind of things, you recover the performance of native fixnums. Maybe you are even willing to trade more values, and typically, if you are using a 64-bit machine, you have actually 3 bits available as the pointers are ending with 0, 0, 0. So you can have fast encoding for more values than simply fixnum and whatever you want. The problem with all that is what happens with flonum. Flonum are specified by this norm, this IEEE norm, and you cannot steal any bit of it. It requires the 64 bits of your word. So if you grab 1 bit, then you lose the library and you will have to re-implement everything by yourself. So somehow, you cannot trade value for space as we did for fixnum. So it looks like we are almost bound to use boxed representation for flonum. Hopefully, some very clever people have noticed a very clever things regarding NaN numbers. And this is the encoding of a NaN value in the IEEE specification. A NaN value is something where you have only 1 in the exponent of your representation and a 1 somewhere. So it means that actually you have 2 to the 52 NaN values available. And if you also observe that on a machine your pointer are restricted to the 2 to the 48 space value, then you realize that you can sneak in your pointer in a NaN value. So you can use NaN values for representing pointer. This is great. So you have plenty of space for storing your pointers, and you also have some available bits for encoding your types. Wonderful trick, just pure computer science. Wonderful. This encoding is optimal for floating points because a float is just a float. What else? Well, the problem it has some downsides. And the downside is that, okay, it takes a little bit of effort to decode your pointer. You have to get rid of all the extra bits. The type checking will be a little bit slow because you have to find where the bits are and to extract them. It works only on 64-bit machine, and it is what I would call a day 1 technique, meaning that if you have already a running system and if it is not prepared for NaN tagging, maybe adapting NaN tagging is not that trivial. So some other very clever people realize something else, is that, okay, instead of favoring floating point, you can favor pointers. And the only thing you have to do is you take a floating point and you add this bias. And by doing that, well, you have shifted all the range, and from now on, your pointers are correctly aligned with just 0 where you want. So you don't need anything else for decoding a pointer now. So it's great, you have recovered the performance of direct pointers, so you have fast object. You have introduced a little slowdown for floats, but maybe that's quite okay. And once again, it only works for 64-bit machine, and once again, it's only a day one technique. What we are proposing is another possibility in this space of implementation of floats. If you consider the space where on the left-hand side you have fast object, on the right-hand side you have fast phloem, you have non-tagging, which is over there, and what we propose is something closer to the fast implementation of objects. So how our technique works? Very, very simple. Let's take a random number, any one. And for in this slide, 3.02. What is the encoding of this number? This configuration of bits. You can arbitrarily say that, okay, this bit pattern now will represent on my system fast phloems. And you have nothing else to do. You just decide that 001 is for fast phloem, and that's it. So you will distinguish fast phloem, which are phloems represented by this bit pattern, to slow phloem. So how will you implement that in C? Well, you will have a predicate that tells you something is a phloem, either if it is a fast one or a slow one. How do you go from something which is an object into something, or the predicate, sorry, is just checking that you have the correct configuration on the right-hand side. How do you go from something which is an object into something which is a double? You just check if it's a fast phloem, you already get the phloem. If it's a slow one, you extract it from its box. And how you go the other way around, you check if the bit configuration of your double corresponds to what you have declared to be a fast phloem. You are done, otherwise you create the box as usual. Wonderful, isn't it? Great idea. So what I've presented is that we are using one configuration of bit, meaning that we have saved 8 of the floating point allocation by basically doing nothing. Great. If 1/8 is not enough, maybe you can go to a quarter of the floating point you want to eliminate, and you can go as much as you want. But whatever you do, this great idea turns out to be a bad great idea, and for this program. Because what you are doing here is that you keep changing your floating points, meaning that you keep shuffling the least significant bit of your float. So your predicate, deciding if something is fast or slow, will keep changing. So you have just killed your branch predictor. So you have saved a lot of memory allocation, but you have bad prediction. So the idea is to use contiguous interval for your fast phloem. And if you're able to do so, you will be safe. How to do that? Instead of using the least significant bit, let's use a bit of the exponent, and we will be done. So what we have conducted is an experiment trying to understand which bit of the exponent we should use. And you see on this table, each possible bit of your exponent, what are the intervals that correspond to this configuration. And we check some benchmark, we check the literature to understand which are the intervals that are meaningful to us. And actually, what we have observed is that there are only 3 intervals that we pay that are useful for us. And these are the 3 intervals that are used there. What you see in this table is the numbers of floating points that are used by each of these programs. And you see that most of the floating point programs are never used. And this is expected because if you consider the last 2 ones, they represent numbers that are bigger than the numbers of particles in the universe. Who cares about that? So if you want to now implement the very fast technique for self-tagged phloem, just implement this predicate, and it tells you if it's one of the 3, then you're done, you have your fast phloem. So we have conducted some experiment, implementing that into real scheme compiler, and we have measured the gain we obtained with that. So the 2 compilers are interesting because the first one is using a kind of slow mark and sweep collector where allocating and claiming object is kind of expensive, and the other one is using bump allocation where we don't have this problem of speed of allocation. And what you observe is that there is no cost associated for non-floating point numbers. So we keep the performance. For the first compiler, by using this technique, we have an acceleration of almost a factor of 2. And it sounds like for the second compiler, we have a little slowdown. But it's actually because our benchmarks are some kind of weird, they are just allocating floating point numbers, nothing else. If you change the benchmark a little bit by just allocating something before running the benchmark, something which is live, then all of a sudden it changes and the two compilers take a huge benefit of this technique. Then we also have compared our technique to NuN-encoding, and you can observe the result here. It's not exactly as efficient as NuN tagging for floating points because the encoding is slightly more expensive, but we have traded simplicity of the implementation for a little bit of performance. So in conclusion, few words about the thing I have not been able to mention today. What you will find in the paper, you will find an efficient implementation of the predicate fast flow num P. You will find an experimental report where we have tested this technique on 4 different microarchitectures. You will find an efficient variant that uses only 1 tag instead of 3, and which you can use on 32-bit architecture. Thank you for your attention.
Okay, for your questions, please come up to the microphone. I already warned you about what I'm going to ask, right? So the chair question, does it also work on other languages than Scheme?
Excuse me, what is your question? I didn't get it.
Have you tried it on other languages than Scheme?
Yes, we have tried, but the reviewer have asked us to remove this experiment that we did, and it was about JavaScript, and we show that we have the same performance improvement on JavaScript, but we have been asked to remove, and we have removed. Thank you for asking this question.
Manuel, can you say something about what you did to the benchmarks to get them to not just allocate floats?
Before entering the benchmark, we allocate something in the heap that is live for the whole execution of the benchmark. That's all. A small prelude, allocate a vector which is live. Nothing else.
Catherine McKinley from Google. Have you thought about how compressed pointers would interact with this, or if you're trying to reduce the floating, make it the floating point number smaller, like a bunch of the approaches in ML now say, we don't need all these precision bits, so how would that work in that setting?
No, we did not. But
next future work?
Maybe not, because in our languages, actually, flow-num are not that important. We really want to favor pointer. It's just that we don't want to have a too inefficient implementation of flow-num. So maybe, but maybe not.
Thank you.
Thank you
nice
for your
work.
question.
Hi, Fabian Murberg, Australian National University. When you evaluated what floating point numbers actually show up, do I get this right, that there are basically no negative floating point numbers?
No, you're wrong. There are negative numbers.
Right, but like you only, wasn't the 111s at the bottom?
The sign is on the left, so I didn't mention the sign, but yeah, we do have negative. We do have negative floating point. Yeah, sure. Okay, thank you.
All right, let's thank Manuel one more time.